Hi, Evan. We're going to review parametrics a little bit. The parametric equations almost always show up in terms of motion along a curve. And so we have a position, x of t, y of t, and you may write it either in angle bracket form or in terms of the unit vectors I and j. The velocity is going to be the derivative of position. So I can literally write that as ds dt, meaning dx dt comma dy dt. If we examine each component separately, then the sign of dx dt will tell me about the motion in the x direction. So for example, if dx dt is greater than 0, then that implies that the object is moving to the right. And if at the same time dy dt is, let's say, less than 0, then that implies that my object is moving down. And if both of these are true, then the object is moving to the right and down. So we can say that the motion of the object would be something like that. If I wish to know how fast the object is going, then I call that the speed of the object, and it is notated as the magnitude of the velocity vector, which of course would be the square root of dx dt squared plus dy dt squared. The acceleration vector is going to then be the second derivative of the position vector, or the derivative of the velocity. So I can write that as either d squared s dt squared or as d dt. And when we did parametric curves, we took our acceleration vectors and resolved them into components that were parallel or tangent to the curve and normal to the curve. AP doesn't push you on any of those details. So that's the difference. So the tangent and normal stuff, I'll talk about it very briefly, but it is not necessary for the AP exam. So this is your optional material. If I have my acceleration vector, then if I create the dot product with the unit tangent vector, then that gives me the tangential acceleration, which tells me the rate at which the speed is changing. And if, on the other hand, I create the dot product with the normal vector, then that gives me the centripetal acceleration, whose value is v squared over the radius of curvature. What's that? That's correct. This is for your information, especially if you happen to be in AP Physics. Centripetal. Yeah, centrifugal. You could just call it A sub n, the projection of A in the normal direction. And so the picture that we would draw is, here's my curve, my parametric curve, and if right at this point, my acceleration vector is like so. My velocity vector will always be tangent to the curve. The velocity vector is always tangent to the curve. Then I can take that acceleration vector and I can construct, first of all, the tangent as velocity over its speed. And then I can construct the normal vector as the rate of change of the tangent vector, like so. So here's my normal vector like that, here's my tangent vector like that, and the projection of A onto the tangent vector is AT, and the projection of A onto the normal vector is A. This page, purely optional material. What is not optional is that often we are asked to define the total distance that an object has traveled. And to find total distance for a parametric curve in 2 dimensions, then we're going to use the same kind of arc length idea that we did for curves that are expressed in terms of x and y coordinates. And we're going to use the same notation that we did for motion in one direction. So our notation looks like this. Total distance L equals the integral of ds, which is the integral of speed dt. Speed is the rate at which my distance is changing. And now I can expand that as the quantity dx dt squared plus dy dt squared, all square rooted. And that's going to be from A to B. And honestly, that's kind of it for parametrics. Seems a lot easier now. I want to take a moment to talk about this quantity ds, which is the differential element of our plane, because that quantity ds can be expressed in several different ways. Obviously, we've expressed it in terms of speed dt for objects that are moving parametrically along a curve. But the ds is fundamentally a geometric quantity. The ds is a little differential piece of arc length right here, and we can write it using the Pythagorean theorem as the square root of dx squared plus dy squared. And now by using a little bit of chain rule, we can express this in one of three ways which are equivalent to one another. One is that we can rewrite dy as dy dx times dx and factor out the root of dx squared. When we do, we get our first expression for ds, which is another way of saying it is root 1 plus f prime squared dx. Are we good with that so far? I could do the same kind of thing, but do it in terms of the variable y. Rather than write dy as dy dx over times dx, I can write dx as dx dy times dy. And if I do that, then I get my arc length in terms of y, which would be suitable if I have a function that is implicitly defined as x equals some g of y. And then the third way is what we've already discussed right here. I could write both x and y as functions of t, so that ds would be equal to dx would be equal to dx dt times dt, and dy would be equal to dy dt times dt. If I factor out square root of dt squared, then I get this guy right here, which just happens to be speed times time. So that we kind of end where we started back in pre-algebra, distance equals rate times time. So be aware of the three different forms that you can use for your element of arc. The green one is ds expressed in terms of the variable t here for a parametrically defined curve.
And that's on the same as
Say again?
I'm just confused with the folder.
Oh, this is unrelated. It's related, but it's not. One obvious question is, what happens if I happen to have a polar curve, right? So I can actually do this. It's kind of a nice result. In that case, I would write this, yes? Okay. So what is dx d theta equal to? Well, dx d theta is equal to negative r sine theta plus r prime cosine theta. And dy d theta is going to be r cosine theta plus r prime sine theta. Now, at first, this looks awful. But when I simplify it down, I'll let you do this on your own to see it. If I expand these squares and add them with a little bit of Pythagorean identity, almost like magic, I end up with this very nice expression right here. R squared plus r prime squared. And I'll let you work that out on your own because without a